Chapter 1.13 Extending Kubernetes. Summary. Kubernetes offers diverse customization options for cluster operators to tailor configurations and extensions without altering core codes. Configurations modify commands, files, and resources but have limitations in managed services. Built-in policy APIs like RBAC are more stable. Extensions expand Kubernetes functions by enabling new hardware and service integrations, often managed by hosted services. Automation, involving controllers, optimizes resource management through the Kubernetes API. Users can extend APIs via custom resources or aggregation layers. Various plugins enhance Kubernetes components like networking and storage. Scheduling extensions involve elaborate setups but are rarely needed. API access extends via authentication, authorization, and dynamic admission control, with customizable webhooks for specific scenarios. Extending Kubernetes. Kubernetes is flexible, needing minimal project code changes. This guide helps cluster operators customize a configuration. Platform developers and contributors can explore extension points, patterns, trade-offs, and limitations. Customization is split into simple configurations and broader extensions. Simple configurations alter command line parameters, config files, or API resources. Extensions require running extra programs or services. This document emphasizes extensions in Kubernetes, aimed at adapting the system to suit different work environments or development needs. Configuration. Configuration and command settings in Kubernetes are documented online, detailing tools like kube-apiserver and kube-proxy. While some settings can be adjusted by the cluster operator, they might change in future versions and often necessitate a restart of processes. Therefore, they're used as a last resort. Built-in policy APIs, such as resource quota and network policy, offer pre-configured controls that are typically available in both self-managed and hosted Kubernetes services. These APIs follow standard Kubernetes conventions, providing stable and supported policy management. Hence, they're preferred over direct configuration changes or command line tweaks. Extensions. The concept of asterisk extensions in Kubernetes asterisk primarily refers to software components that expand the capabilities of Kubernetes, enabling it to support new data types and hardware. These extensions come pre-installed in many distributed instances of Kubernetes, making it uncommon for users to install or create new extensions themselves. Automation asterisk plays a significant role in Kubernetes, facilitated by client programs that interact with the Kubernetes API. This automation can seamlessly operate on or off the cluster, ensuring robust and reliable operations across various environments, including hosted and managed clusters. The asterisk controller pattern asterisk is a common strategy for writing client programs in Kubernetes. Controllers connect with the Kubernetes API to read object specifications, perform tasks, and update object status accordingly. When Kubernetes itself acts as a client, it utilizes webhooks to make synchronous HTTP callouts to remote services for notifications or actions. Within Kubernetes, there are a variety of asterisk extension points asterisk demonstrated through a diagram of the overall architecture. These points enable customization of client behavior, API requests, and content handling. Specific extensions allow adjustments to scheduling decisions, plugin executions, and API server request handling. The asterisk role of kubelet asterisk asterisk in Kubernetes is to operate on nodes, ensuring pods are displayed as virtual servers. Different plugins, such as network and storage plugins, enable diverse implementations of pod networking and storage, making it possible to integrate custom hardware and node local features within a cluster. To determine the best approach for using extensions in Kubernetes, users can refer to a asterisk flowchart. This guide can simplify the decision process because multiple solutions may involve utilizing various types of extensions simultaneously. Client extensions. Kubectl plugins are separate add-ons that enhance or replace specific commands of the kubectl tool, typically focusing on local user environments. These plugins can also integrate with credential plugins, but they don't apply broader changes to site-wide policies. To learn how to use plugins with kubectl and expand its capabilities, refer to the guide on extending kubectl with plugins. API extensions. Custom resource definitions are used to define new controllers or configuration objects in Kubernetes, which can be managed using tools like kubectl. The API aggregation layer helps integrate additional services into Kubernetes, like metrics, expanding the Kubernetes API capabilities. A combination of custom resource APIs and control loops forms the controllers pattern. It replaces manual operations with automated processes following the operator pattern. Custom APIs can manage resources like storage or define policies. Adding custom resources creates new API groups, not altering existing APIs, though extensions can. API access extensions. When a request reaches a Kubernetes API server, it is authenticated, authorized, and subjected to admission control. Unauthenticated requests are treated specially. Authentication maps request headers to usernames, leveraging built-in methods, authenticating proxies, or authentication webhooks. Authorization determines whether users can access API resources like reading or writing. Unlike object fields, it's focused on whole resources. Custom authorization is possible with webhooks if built-in options don't suffice. In dynamic admission control, requests undergo further steps post-authorization, especially write operations. Built-in and extension options like the image policy webhook limit container images, while admission webhooks allow broader decision-making and can modify requests before further processing. The entire process of authentication, authorization, and admission control can be customized using extension points and webhooks to suit specific needs that built-in features can't address. By understanding and configuring these security and control layers, Kubernetes manages API requests comprehensively and securely, ensuring proper resource access and management. Infrastructure extensions. Device plugins help nodes in Kubernetes recognize new resources, like additional hardware, beyond CPU and memory. Storage plugins, particularly the Container Storage Interface, CSI, expand storage capabilities by supporting various types of volumes, including external and ephemeral storages. Kubernetes originally supported Flex volume plugins for mounting non-default volumes, but they're deprecated since version 1.23, now replaced by CSI. Flex volume required running a binary plugin plus for mounting. More details once existed in an archived design proposal. Network plugins ensure proper networking within Kubernetes by accommodating different network types. Kubelet Image Credential Provider plugins enable dynamic retrieval of image registry credentials for container image pulling since version 1.26. Scheduling extensions. The Kubernetes scheduler assigns pods to nodes and allows customization through plugins, profiles, and extensions. Users can replace the default scheduler or run multiple schedulers, but most users don't need to change the scheduler. You can enhance scheduling with plugins or webhooks that filter and prioritize nodes for pods, using Kube Scheduler's extension points.